Problem number 9, we have a buffalo stampede. It is following, it has this vector field here in this region right here. And so we want to use this information to figure out the net flux of buffalo leaving or entering this region here. So some of them are entering down here, some of them are leaving up here. The net flux out of this square right here. How do we do this? We use the flux divergence form of Green's theorem, kind of like a 2D version of the divergence theorem. That says the integral over the boundary of our region D here of f dot n ds is equal to the double integral over D itself of the divergence of f. So this is the flux. This is what we're asked to find. Instead, we're going to calculate out the right side here. What is the divergence of f? The partial derivative of this respect to x is y. The partial derivative of this respect to y is 1. So we are integrating. Our integrand is y plus 1. And x and y bounds are both from 2 to 3. If you crunch this out, you get 3.5. Okay, but then we are told that there's a density of rho is 500 buffalo per square kilometers. There is, this region in question is 1 square kilometer, so we have to multiply our final answer by 500. So this would be what, 1,750 buffalo are leaving. It's positive, so they're leaving D per minute overall. Okay, so that is problem number 9, a fun little problem. Problem number 10, we want to verify Stokes'S theorem for the vector field given right here, the upper unit hemisphere given right here, and then repeat the question for the lower unit hemisphere. Both of these are going to be oriented pointing outward. Okay, so when we say verify, this is the picture that we should be having in mind. We want to, so we want to calculate both sides. We want to calculate the double integral over the surface S of the flux of the curl of F. And we also, I guess I'm putting this in the opposite order how I usually do it, the circulation of F itself along the boundary. So what do we need to do here? Well, one thing is that we need the curl. So let's go ahead, compute the curl. I hat, j hat, k hat, partial derivatives with respect to x, y, and z, and 2y plus z, and 3x, and x plus z. Okay, so what do we end up with? We end up with the partial derivative with respect to y of this is 0 minus partial derivative with respect to z of this is 0. The partial derivative with respect to z of 2y plus z is 1 minus partial derivative with respect to x of x plus z is 1. And then we have the partial derivative with respect to x of 3x is 3 minus the partial derivative with respect to y of 2y. Okay, it's 2. This is the vector 0, 0, 1. Okay, so that is one calculation we'll have to do. Let's go ahead and compute out the left side here. So how do we parameterize this? Our parameterization in terms of phi and theta is cosine theta sine phi, sine theta sine phi, cosine phi. And the normal vector that you end up with when you take the cross product of r phi cross r theta ends up as this times a factor of sine phi. So cosine theta sine squared phi, sine theta sine squared phi, cosine phi sine phi. And when we do, let's see, so we have to substitute in our parameterization to the integrand for the left side here, but this is just a constant integrand, so that doesn't change anything. So now we have to do the curl of f dot product this normal vector, this dot product, this will give us 0 plus 0 plus cosine phi sine phi. So now, what do we have for the left side here? Integral of the curl of f over the surface. So for this, phi will run from 0 to pi over 2. And then theta will run from 0 to 2 pi. We're integrating cosine phi sine phi d theta d phi here. And if you crunch this out, I'm going to skip over the details. You get pi as your answer. So now, what do we have to do? We have to evaluate this over, we have to evaluate the line integral along the boundary here. So to parameterize the boundary, how many times have we done this kind of parameterization? Cosine t sine t 0 here. That's the parameterization of the boundary. And let's see here. So a derivative r prime of t, negative sine t, cosine t, and 0. Now we have to substitute in r of t into, not into the curl, but into our original vector field. F of r of t is 2 times y, 2 times sine t, plus z is 0, 3 times cosine t, and then cosine t plus 0. And so when we compute the dot product here, f dot product r prime ends up as negative 2 sine squared t plus 3 cosine squared t. So the integral from 0 to 2 pi of this, negative 2 sine squared t plus 3 cosine squared t dt, also ends up as pi. And so that checks out. Okay, so that is problem 10. It says to repeat the question for the lower hemisphere. So when you repeat the question for the lower hemisphere, let me just comment on the only things that change. So both sides end up as negative pi. So down here, for the flux of the curl of f, the only thing that would change is now our bounds on phi would be from pi over 2 to pi, instead of from 0 to pi over 2. And so that would make, that change makes this negative pi. And then what ends up happening is that we have to orient our boundary going in the opposite direction, clockwise. You flip cosine t and sine t, and that ends up flipping the sign down here. So both end up as negative pi. You can check that for yourself.